Hi, welcome to Lesson 16C, Stationary Points. The goal of today's lesson is to use knowledge of gradients of tangents to determine where stationary points of curves occur. So the first thing we need to know is, what is a stationary point? Well, basically, curves increase and decrease, as we saw in previous lessons, and if we see a curve increasing, so if the curve is increasing, then we know that the gradient function is going to be positive. So the gradient is going to be positive when a curve is increasing, of course, and when a curve is decreasing, then that means that the gradient function is going to be negative. Okay, so we're looking at some sort of curve, in this case like this, and the tangent, if that hit properly, which it didn't, the tangent is positive. It's increasing because the curve's increasing, therefore the gradient of the tangent is positive, and on this side the tangent is negative because the curve is decreasing at those points. Okay, well, what happens in between? Well, in between it's neither increasing nor decreasing. That's where the derivative, the gradient function, is actually 0. So that's where we get a horizontal tangent. So if we had a tangent, here the tangent is positive because it's going up to the right. Here the tangent is negative, is going down to the right. And here, right at this point right here, that's where the derivative is 0. That's where the tangent is horizontal. The gradient of the curve at that point is 0. There's no inclination to speak of besides 0, so it's not increasing nor decreasing. So therefore, that's where what we call a stationary point. So at that stationary point, we know that the derivative is 0. Okay, so that can be very helpful to us to help us when we're sketching curves. We need to know when the function is changing its curvature, so it's changing from increasing to decreasing and vice versa. And we can also see where the concavity changes. So what we can do is, when we take a look at functions like this, for example, we see that there's a local maximum here, and here is right where the gradient is 0. The tangent is horizontal, so the gradient of that tangent, and therefore the gradient of the curve, is 0 right at that point. We also see down here at the local minimum that the gradient is also 0. Right, there's the horizontal tangent. Those are both called turning points, where the curve turns and goes from increasing to decreasing, or from decreasing to increasing. Okay, and then there's another spot where there is a horizontal tangent, and that's what's called a stationary inflection point. And the stationary inflection point, well, first of all, an inflection point is where the concavity of the curve changes. Here it's concave down. Okay, so concave, like a true concave down, would be something like this, right? It's concave down. Concave up would be if the curve is like that. Okay, so it's opening up or opening down. Concave up is this way, concave down is this way. Where the concavity changes, here is concave down, and then here on this side is concave up. So between the changes in concavity, right in the middle, is what's called an inflection point. And the stationary inflection point is where that the tangent through that point is actually horizontal. Because generally a tangent will kind of ride on top of the curve as it gets closer and closer to the inflection point, and then afterwards it rides below the curve if it's concave up. So right in between that tangent, even though it does cut through the graph, whereas normally it just kind of touches it, this is one instance where it'll actually go through the graph and in this case it's horizontal. So that's a stationary inflection point. So we have turning points, a local maximum or a local minimum where the tangent is horizontal, and then we have a stationary inflection point where the concavity changes here from concave down to concave up, but also could be from concave up to concave down, and we'll also have a stationary inflection point in that case as well. So if we're looking at sine diagrams, I'll just flip the page here. If we have sine diagrams like this, we can have a local maximum like we just saw, and maybe I'll just reference this, a local maximum here on the left side of that value, x equals a. Here it's x equals -2. We see that the derivative function is positive because it's increasing. The derivative is increasing. The slope of the tangent, the gradient of the tangent is increasing. It's positive. Therefore, the actual function is going to be increasing like this. On the following side, or the side after, to the right of this point, x equals a, if the gradient is negative, that means that the function is decreasing. So you can see actually just by drawing these two arrows here, we can see that it actually takes the shape of the curve as we go around through that local maximum. Okay, and then this just kind of verifies that this is what the graph would look like in this case. If we were to go around a local minimum, well, again, the same sort of idea. In this case, now we're looking at this local minimum right here in this graph, where the derivative function is negative, the actual function, the graph of the function is decreasing, and where the derivative function, the gradient function is positive, that's where the graph is increasing, and we see that we have that curvature here, which mimics this curvature, and that shows that there is actually a local minimum there. And right at x equals a in both of these cases, there's going to be a horizontal tangent. So here there's a horizontal tangent right there at x equals a, and right here at x equals a. In this case, looking at these two at x equals -2 and x equals +1. And then for a stationary inflection point, we see that where the derivative function, the gradient function, is positive on both sides, that means that the function itself is increasing on both sides. Like in this graph, the function is increasing here, and then it goes to 0. It doesn't increase right there, and then it continues increasing. So it's increasing on both sides, like we have here, like is diagrammed here, on either side of the inflection point, and here, in the second case, where the derivative function, the gradient function, is negative on both sides, the actual function is decreasing on both sides, therefore it's going down, it's decreasing on both sides of that stationary inflection point. Okay, so if we were to see the actual sine diagram for this curve, we see that the gradient function is positive here. The gradient of the tangent is positive. That means that the function is increasing. Here, the gradient function is negative, so the gradient of the tangent is negative between those 2 points, and therefore the slope, or the function itself, is decreasing. On this side, the gradient again is positive. The gradient function, the derivative, is positive. The function is increasing, and on this side, the gradient function again is positive. The function itself is increasing again. Okay. Now, one thing that's not shown here, we'll get to this in 16D, is halfway between this local maximum and this local minimum. Well, you see, here's concave down here. This is concave up. Well, halfway between these two, horizontally, halfway between these two, will be another point of inflection, not a stationary point of inflection because the tangent is not horizontal in this case, but there is another point of inflection where, again, the concavity changes from concave down to concave up, and that happens halfway between a local maximum, a local minimum. But we'll touch on that more in lesson 16D. Okay, so we're going to look at a few examples tomorrow in class, and in the meantime what I'd like you to do is take a look at example 11 on page 398. Look through example 12 and 13 on page 399, and please don't hesitate to click on the self-tutor to have her explain the solution of those examples to you. And then I'd like you to peruse through exercises 1, 2BDFI, 4ACD, 5, 7, 10, and 11 on page 400. Okay, and that'll get you all primed and ready to go before tomorrow's work through of examples. Okay, well, thanks for watching, and we'll see you in class.